Hello everyone, myself Dr. Ashish Choudhury from IIIT Bangalore. I will be offering a course titled Secure Computation Part 2, and in this short presentation I will be discussing about course overview, learning objectives and learning outcomes. So, there are several real world distributed computing tasks where there are multiple parties who are mutually distrusting, and each party has some private input which the party would not like to disclose to the other parties, but at the same time the parties would like to perform some joint computation on their data without revealing the data to the other parties. So, this problem is often called as computing on private data or secure multi-party computation, or MPC in short. And if you are wondering that can we solve this problem using encryption schemes, and then the answer is no, because if each individual party just encrypts its data, then it ensures that the data remains confidential, but at the same time we would require the parties to perform computed on the encrypted data. With the current technologies available, it is difficult to do so. So, we require different approach to solve this problem. So, this secure MPC is a very powerful abstraction because there are several real world problems which can be abstracted by this powerful abstraction. For instance, if we have a set of hospitals in the city who would like to carry out some kind of data mining operation across the medical records of all the hospitals, then that is captured by this abstraction. Of course, it is possible for the hospitals to perform any kind of data mining operation if they make public their individual medical records, but medical records are very sensitive. So, no hospital would like to make public its medical record. So, what we require here is a protocol which can allow the hospitals to collaborate, and without revealing their individual medical database, they should be able to carry out whatever data mining operation they would like to perform. So, for instance, they might be interested to find out is there any common patient registered across all the hospitals, or they might be interested to find out the count of total number of patients suffering from a particular disease and so on. So, how MPC captures this real world problem? So, in this example the participants will be your hospitals, and the inputs x1, x2, xi, xn models your individual medical records, and the function f will model whatever data mining operation the parties would like to perform. Or you can take the secure online dating problems where we say we have two parties, or Alice and Bob, and they would like to find out whether they are mutually interested in each other or not. Okay. Of course, they can tell this to the other party or the other person on face, but that may not look good. So, what they would like to do is that they would like to run a protocol where at the end of the protocol they find out whether both of them are mutually interested in each other or not, without revealing anything additional about their mutual preferences. Or we can take a scenario where we have a sample held by a client, and we would like to check whether that sample belongs to a huge database. Okay. So, this is a client server scenario. Of course, if the database is public and if the client sample is public, the problem is easy to solve. But what we would like to do here is that without revealing the client sample and without revealing the individual entries of the database, we would like to check whether the sample of the client belongs to the database server's database or not. So, again this problem can be abstracted by this secure MPC problem. Or we can have a scenario where we have say big data owners, tech giants, who would like to collaborate to construct a machine learning model, but in a privacy preserving fashion, in the sense that the data held by the individual data owner should not be leaked to the other data owners. So, all these problems can be abstracted by this wonderful problem of secure MPC, which is a very fundamental problem in secure distributed computing. As you can see, if you have a solution for this general problem, then you have a solution for various case studies which I have shown in this slide, and there are several other problems as well which can be abstracted by this powerful abstraction. So, there are various dimensions to study the MPC problem depending upon how do we abstract the function, whether the function is abstracted as a Boolean function or whether it is represented as an arithmetic circuit, depending upon what is the type of the network through which the participants will be communicating in the protocol, whether it is synchronous or whether it is asynchronous, and how do we model the distrust in the system. So, the distrust in the system is going to be modeled by an adversary, but there are various ways to model the adversary depending upon its corruption capacity, its running time, and when exactly the adversary is going to corrupt the participants in the system, what type of corruption is there, and so on. So, I had already offered a course titled Secure Computation Part 1, which is available here, and in that course we had discussed only passive corruptions or semi-honest corruptions, which are also called as honest but curious setting. And passive corruptions means that the corrupt parties, namely the parties which are under the control of the adversary, they will follow the protocol instructions, but at the same time they would like to collaborate and try to infer additional information regarding the inputs of the remaining parties. And in that course itself we had seen several challenges which we face while dealing with such an adversary, and in that course we had seen various seminal results regarding passive corruptions. But in real world scenario, the adversary may not be always passive. Adversary may cause the corrupt parties to deviate from the protocol instructions arbitrarily. So, for instance, the adversary can crash the corrupt party at any time during the execution of the protocol. It could be in the middle of the protocol, or the adversary could enforce the corrupt parties to start sending arbitrary values in the protocol. So, such adversaries are modeled by active adversaries, which are also called as Byzantine corruptions or malicious corruptions. So, the focus of this course, maybe the part 2 of the course, will be on active corruptions or Byzantine corruptions. And you might be wondering that are there any serious challenges while considering Byzantine adversaries? And answer is yes. Even simple tasks become very challenging when we go to active adversarial setting. So, to give you a flavor of that, consider a very simple problem, namely that of broadcast. You have a sender party here, namely one of the parties is designated as a sender, and it has some message which it would like to send identically to all the parties in the system, even if there are up to say t corrupt parties in the system. And we do not know which t parties could be corrupt in the system, and we also do not know whether the sender could be corrupt or not. So, now if I model the corruption as a semi-honest corruption or passive corruption, then a simple protocol to broadcast a message will be to ask the sender to just send its message to everyone. Now, in this protocol, even if the sender is potentially corrupt, it will not deviate from the protocol instruction, and it will send an identical copy of its message to all the participants in the system. But what if I run this protocol assuming a malicious adversary or active corruption? In this case, if the sender is corrupt, and remember we do not know whether the sender could get corrupt during the protocol execution or not, because we do not know which t parties the adversary might decide to corrupt. So, if I model the corruption as an active corruption, and if the sender gets corrupt, then this protocol simply breaks down, because what the corrupt sender can do is it can send different versions of its message to different parties. So, this simple looking protocol simply fails here, and now on top of this simple protocol we require additional mechanisms which should allow the parties to agree upon a common output. So, even a simple task of broadcasting a message becomes non-trivial when we go to the active corruption model. So, what are the topics which we are going to cover in this course? We will see some classical distributed consensus or agreement protocols. So, informally in a consensus protocol we have the participants with some private inputs. To begin with, the parties may not know the inputs of the other parties, and there might be a subset of parties which could get corrupt during the protocol execution by a Byzantine adversary or a malicious adversary, and the goal is to ensure that at the end of the protocol all the honest participants or all the participants who are not corrupt have a common output. That means even if all the uncorrupt parties start with different set of inputs, at the end of the protocol they should have a common output. So, that is a consensus problem. There are several classical consensus protocols which we will discuss in this course. So, consensus is one of the fundamental problems in distributed computing. Recently it started grabbing the attention of several other communities apart from distributed computing after the advent of blockchain technologies. The second problem or the topic which we are going to discuss in this course is that of verifiable secret sharing. So, in the secure computation part 1 course we had seen Samir secret sharing, a very simple secret sharing scheme which allows a designated party with some secret S to share its input among the participants in such a way that only when a certain subset of parties or shareholders pool together their shares, they will be able to recover back the dealer's secret. But if those many number of shareholders do not come together, the dealer's secret remains private. So, the Samir secret sharing scheme achieves all the required properties assuming passive or semi-honest corruption. But if I take the Samir secret sharing protocol to the malicious adversary setting, then the protocol simply fails, because if the dealer is potentially corrupt, then it may not secret share its input consistently as per the Samir secret sharing protocol. So, what we require here is a verification mechanism on top of this Samir sharing protocol to ensure that even a potentially corrupt dealer has secret shared its input properly, consistently. And during this verification, the challenge is that if the dealer is honest, then the verification should not end up leaking the dealer's secret. So, there are several challenges involved as part of this verification mechanism. Another problem which we will discuss in this course is that of secure message transmission, where we have a sender and a receiver who are part of a distributed communication network, and they are connected through several disjoint channels or paths, and sender has some message which it would like to securely communicate to the receiver by communicating over these channels. But the challenge here is that there might be a subset of channels which might get corrupt during the execution of the protocol, and which channels may get corrupt we do not know beforehand. So, how we can solve this problem? So, that is another topic which we are going to discuss in this course, and of course, by stitching together all the primitives which we are going to discuss in this course, we will solve the problem of secure multi-party computation. We will see how we can design maliciously secure MPC protocols, where even if a subset of participants get maliciously corrupt, the uncorrupt participants end up learning the correct output without disclosing anything additional about their respective inputs. So, the background required for this course is the following. So, we expect the participants should be comfortable with basic concepts in probability theory, discrete mathematics, and algorithms and data structure. Prior knowledge for the following topics will be an asset. If you are familiar with basic concepts in cryptography, then it will be very good, but do not worry if you do not know too much of cryptography. You can always go through an NPTEL course on foundations of cryptography. You can go through the lecture videos, and it is preferred that you have, if you have done the secure computation part 1 course. But at the same time, I would like to stress that full effort will be made from my side to keep the course self contained. Okay, so even if you have not gone through the secure computation part 1 course, that is fine. The expected course objectives and outcomes are the following. This course aims to cover the formal details of this topic and expose the participants to the fundamental results of the topic. And we hope that at the end of the course, participants will be able to understand a significant portion of MPC related research papers, specifically maliciously secure MPC. A brief introduction about me: I am an associate professor at International Institute of Information Technology, Bangalore, and you can find more about me from my personal home page. My training is on theoretical computer science with specialization in cryptographic protocols. I have been teaching courses on discrete mathematics, basic cryptography and advanced cryptography over the last 6 years, and these are some of the courses which I had offered earlier on NPTEL. So, with that I end this introduction video, and I welcome you all to this course. Thank you.